Then we're going to go ahead and talk about AFCS. Now, in talking about the AFCS, this is where you're going to get excited because this is what's going to reduce your workload by 87%, give or take a percent or two. And that's a heck of a workload reduction. Okay, you're going to find out that this system is going to provide for everything that you need short of one thing that you would want. What?
Coffee.
Actually, in some cases we have that, sir. Okay, I know on my bird we did. No. The only thing we lack is one card connecting a navigational system to the advanced flight control system. If we had that, we would have an autopilot. We lack that one card. But we have everything else short of that. Okay? Now, as we look at the advanced flight control system, terminal learning objective, action, describe, components, operational characteristics, limitations, operational procedures, and emergency procedures of the CH-47D Advanced Flight Control System, AFCS for short. Conditions in a classroom given a CH-47D Advanced Flight Control System trainer or student handouts. Standards, correctly answer in writing without reference. 14 of 19 questions pertaining to the components, operational characteristics, limitations, operational procedure, and emergency procedures of the CH-47D Advanced Flight Control System, AFCS, in accordance with TM 1-1520, 240-10, and the student handout. Safety requirements, none. Risk assessment level, low. Environmental considerations, none. Evaluation. Each student will be evaluated on this block of instruction during the first written examination. This will be a criterion type examination requiring a go on each scored unit. You will have 90 minutes for the exam. Any questions? Describing the AFCS. In looking at the components, it's going to consist of two completely identical systems. Two completely identical systems. Up in the cockpit, you have your control panel located on the candy console, right-hand side, closest to the pilot. You also have your master caution / advisory panel. PDP for electricity, which stands for power distribution panel. You have your components in the flight control closet, and we'll talk about all those components again. We've actually already covered them under flight controls themselves, but we will talk about them, we will show you them. Your proximity switch landing gear. On your landing gear, you have two identical computers. Both computers are completely identical. And then, of course, your cyclic and thrust control. We're going to talk about all of those. As we look at your identical systems, every axis of the aircraft is going to be controlled. Every axis of the aircraft is going to be controlled. And they're going to provide for stabilization or motion dampening. They're always going to provide for that. We had that on the earlier models, we had that on the D model. And all we did was enhance that. My Black Hawk people, you're going to find out that this system, although it has some similarities, is actually going to provide for more features and more functions compared to what the UH-60 offers. And so you will have some differences. What's it going to provide for other than stability about all axes? It's going to provide for bank angle hold, which is going to seem really weird. Why? Because basically, you can put this aircraft into a bank, and it's going to maintain that bank angle forever and ever, amen, until you either tell it otherwise or it runs out of gas. And the freaky thing about it is once you put the bank angle in, it's going to mechanically neutralize your control back up again, which is going to seem really weird. But if you think about it, if you were to put an aircraft into a bank and just hold that bank, what would the ultimate result be in the aircraft? It would roll right over, but not in this one because we have bank angle holding. We're going to talk about how that's accomplished. Okay. Now, the next one we're going to talk about is heading hold. Now, as we look at heading hold is what we classify as a automatic feature, meaning what? Meaning as long as the advanced flight control system is on, you are going to have heading hold. And how that's going to be provided for is in the avionics closet, you have your directional gyro. That directional gyro signal is going to go directly to the advanced flight control system. And then because it's heading hold, it's going to go to your yaw integrated lower control actuator. We call them ILCAs for short. And it's going to maintain the heading of the aircraft for you. Now, bank angle hold and heading hold are automatic features, meaning what? Meaning as long as the advanced flight control system is on, you're going to have those features. You don't have to do anything special. You don't have to push any additional buttons. You don't have to set it up. Any questions about that? Okay, now, that should take you through A, B, and C of your handout so far. What I'm going to recommend you do is with D, E, and F, put one of these doohickeys and write dash. Differential airspeed hold. That's what dash stands for. Now, the first one on there is airspeed hold. Airspeed hold is going to be provided for above 40 knots. Airspeed hold is going to be provided for above 40 knots. The next one is pitch attitude hold. Now, if I maintain pitch attitude of the aircraft, essentially what am I still maintaining? Airspeed. Okay, so now, in talking about that, what's the difference? Why do I have the difference? What do I know about airspeed? How is airspeed derived? From what system? What do we use? What does the aircraft use? What?
Pitot-static.
Your pitot-static system. And if you haven't had it emphasized to you, the pitot-static system on this aircraft is unreliable below 40 knots. Period. Okay? So that's why we have to be above 40 knots for that to kick in. And we'll talk about how it works and get into the nitty-gritty as we go along. Okay? So now, that's what the system's using when we're above 40 knots. Below 40 knots, it's going to maintain pitch attitude of the aircraft. What do we have on the aircraft that will display and create signals proportional to the pitch angle of the aircraft? What component do we have that will do that?
You have your LCT.
No. Not what I'm looking for.
Attitude.
Okay, what feeds the attitude indicator?
Gyro.
The gyro. In your avionics closet, you have vertical gyros. They are going to send a pitch attitude signal to the advanced flight control system to maintain pitch attitude. Now, let me ask you this. In maintaining pitch attitude, essentially I'm still maintaining what? Airspeed, how fast we're going. But now, why can I use pitch attitude below 40 knots. Why can't I use pitch attitude above 40 knots? Why do I have to have one system above 40 knots, one system below 40 knots? Why can't I use pitch attitude hold above 40 knots?
The aircraft trying to level itself at
Via what?
the LCT.
Via the LCTs. So this aircraft is going to fly level as we increase our airspeed above 40 knots, so therefore there's not going to be a pitch attitude of attack on the aircraft. So that's why, in order to maintain airspeed through all modes of flight, essentially is what we're doing, we had to have the two different methods. Hence, differential airspeed hold. That is the job of the dash actuator, is to maintain how fast we're flying. It's just using two different processes to do it, based on known facts. What? PDOT static system's unreliable below 40 knots, and the aircraft's going to level itself off at airspeeds above 40 knots, so therefore they had to have the two different systems. Now the next one is positive stick gradient. And people like to complicate positive stick gradient. All positive stick gradient is the ability to put in a forward stick position and leave it. That's all it is. Nothing more, nothing less. Okay? The one they like to use, and it's okay to use because it's pretty good, pretty accurate to go by, is if you put a 1-inch stick position into the Cyclic, you're going to maintain approximately 100 knots. And you don't have to sit there and do what would you normally have to do to maintain 100 knots? Put it in, take it out, put it in, take it out. No matter how slight it is. Okay, and I think we already pretty much talked about the opinion about the sweet spot. I'm not going to argue about a sweet spot. Okay, not my job. But my job is to help you understand that normally, in order to fly any aircraft and maintain airspeed, you're going to be sitting there, and you personally as a pilot are going to be correcting for forces acting on the aircraft to help you maintain it. Now ideally, if winds don't change, inputs and forces acting on the aircraft don't change, you should be able to find a position and leave it and maintain airspeed. But because forces are always constantly changing, the aircraft's going to have to be changed. Only in this aircraft, you got the differential airspeed hold actuator doing it for you, which is why you don't have to put it in, take it out, put it in, take it out, put it in, take it out. But now, if I turn this system off, guess what this aircraft flies just like? Any other aircraft. Any other aircraft. How many have already gotten to turn off the AFCS in the box? Anybody? Okay. The first time they turn it off, it's going to be interesting. Okay? And I'm going to try to prepare you for when it gets turned off, because there's some features and some support that you're getting from the computer that's going to go away. And when it goes away, if you don't know to prepare for it, the aircraft's going to get ahead of you. And we'll make sure that you're prepared for that. Any questions about those? Okay, next, what we're going to talk about is your AFCS trim. And we kind of already talked about that. What did we say AFCS trim was?
Mag brake.
Not the mag brake. AFCS trim is the ability to turn this aircraft using this switch right here. This is your AFCS trim switch. You can roll this aircraft through the entire limits of its bank angle simply by using this switch. Now, they will, for training purposes, they will show you how to roll this aircraft into a turn using the AFCS trim switch. It's not how we normally use it. You're not going to use the AFCS trim switch to roll this aircraft into any major bank. But it is capable of it. And what they're going to use it for and why they're going to do it is because when you use the AFCS trim switch to turn the aircraft, this stick position is going to remain perfectly still. because this signal is going through the AFCS computer to the roll extensible link portion of your integrated load control actuators. Now, keeping in mind that the AFCS trim switch not only works laterally, but it works longitudinally. But keep in mind, what did we say about longitudinal AFCS trim switch? It is not a feature of AFCS. It was a direct relationship between this switch and what? The cockpit control driver actuator in the flight control closet. But because the switch is called AFCS trim, that's where the confusion comes in, and we'll re-emphasize that as we go along. Any questions about that? Okay, now, the next thing we're going to talk about is heading select. In talking about heading select, we really have already talked about it. All we have to do is remind you, because we've really kind of already did this before. We just did it a little different way. Now this directional gyro signal has to go where? Your HSI? Your horizontal situation indicator? Now, which HSI is it going to be using? Whichever one has command select. Keep that in mind. So here's my command select button. Now I'm going to take my heading knob, line up my heading bug with wherever I want it to go, and then when I push heading select on the AFCS control panel, now what's going to happen is the aircraft's going to be maintained by the AFCS based on a signal created from your HSI to the AFCS computers, and now it's not only going to go to your yaw ILCA, but it's also going to go to what? Your roll integrated lower control actuator. Why? Because when I rotate that knob and I cause this heading bug to move, I create an error signal between the bug and that lubber line, and now the aircraft is going to make up to a standard rate coordinated turn, roll the aircraft out onto the new heading, and maintain the new heading. Any questions about that? Any questions? Okay, and then last but not least is your LCTs. Your LCTs are programmed and maintained by the advanced flight control computers when you are in what mode? The LCTs can be operated in how many modes?
Auto and manual.
Auto and manual. So when you are in the automatic position, what is happening is the AFCS computers are going to be maintaining and programming those longitude cyclic trim actuators for you. Why are they going to be programming the LCTs? To do several things. One, level off that fuselage. Programming the tilt in the rotor system, leveling off the fuselage, making a bus as aerodynamic as a bus can be. Because it's programming the forward LCTs, programming cyclic tilt, that's also what's going to reduce blade flapping. And by reducing blade flapping, reducing the angle of attack on the fuselage, reducing fuselage drag, it's going to allow for the higher V&Es with less stress on critical components, the rotors, and in specifically the aft vertical shaft. Yes, sir.
For the LCDs to kick in during a hover, They're attached to the sensors in the shocks.
On the aft landing gear, yes sir. They have a proximity switch, which we're going to talk about today.
Okay, and what happens if you're just hovering on the back two wheels? They stay on the ground?
Yes sir.
They maintain the ground.
They maintain the ground position, but remember, right now, how are you controlling the aircraft when you're two-wheel taxiing?
Steering control.
Thrust control. Thrust control. That's what's actually going to be determining whether this aircraft goes forward, or if you pull in more power, it goes backwards.
Even in the water, same thing?
In water, because the proximity switches are not working, your LCTs are going to remain as if they were in flight. So they're going to stay retracted until you manually extend them or retract them. Or they'll go retracted automatically because of the proximity switches. But you're going to have to manually extend them if you want to go forward. And the thing about it is you can put in forward and aft cyclic, but reality is, what are we creating when we put in forward and aft cyclic? Differential collective pitch. So reality is, it's more with the LCTs and than just power alone. Because if you just do power alone, because you're in the water, it's really not going to do too much. So you're going to have to maybe mess with those. Any other questions? Looking at the AFCS control panel. Before we get into the AFCS control panel, on page 5 of your handout, you're going to notice we're going to talk about the requirements for the AFCS. Requirements are going to be AC and DC power. AC and DC power. Number 1 electrical system is going to provide the electrical power for the number 1 AFCS computer. Number 2 electrical power is going to provide it for the number 2 AFCS. Now keep in mind, when we get into electrics, we'll get into a little bit more information on electricity. But right now, number 1 system controls the number 1 AFCS, AC-DC. Number 2 system, AC-DC, controls the number 2 AFCS computer. It requires both vertical gyros. The one vertical gyro is going to provide a signal for the number 1 AFCS computer. The number 2 vertical gyro is going to provide it for the number 2 vertical gyro, or AFCS. Keeping in mind that the number 1 vertical gyro is feeding which vertical gyro indicator? The co-pilots. The number 2 vertical gyro is feeding the pilot's vertical gyro indicator. Why? Because it cares about the side of the aircraft, not the title of the individual sitting in the seat. Any questions about that? And then last but not least, it requires flight control hydraulics. Number 1 flight control hydraulic is going to provide for the number 1 AFCS system. Number 2 flight control hydraulics is going to provide for the number 2 AFCS system. Any questions about that? Bull leg 4, we talked about under flight controls that with both systems on, both systems are going to be moving at 100%, providing for the required input. If one system is turned off or selected off or starts to malfunction and we turn it off, then the one system will provide for the entire control movement. And we talked about that 3/4 gain. Keeping in mind, gain is nothing more than an electrical term. It has no business being in R-10. Because what you need to know as a pilot is that if we are operating on a single AFCS, the 100% required input that you're asking for is going to be given to you, and it will, through a single AFCS system. Any questions about that? And then that's where we drew that drawing up on the board with the summing link and how it's compensated for? Does everybody remember that? Okay. AFCS control panel we said was located on the can of cancel, right-hand side, closest to the pilot. It's going to consist of a 5-position rotary switch. 5-position rotary switch. You got an off to the left, off to the right, number 1 system, both, number 2 system. Off to the left, number 1, both, number 2, off to the right. Question that comes up and that will always be asked is, why 2 offs? Why do we need 2 offs?
Because if you want to turn it off and you got one of the 2 systems selected, you don't want to go through the other system if it's malfunctioning to turn it off.
Exactly. They gave you the ability to not have to transition back through a bad system to get to an off. That's why we have 2 offs. Now, when I turn the AFCS off, what am I turning off? What?
The hydraulics?
Ah, very good. Does everybody hear that? When I turn off the AFCS, the only thing I am doing is turning off the hydraulics to your integrated lower control actuator, and I'm turning off the dash electrically. I'll say that again. When you turn the AFCS off, and under flight control hydraulics, Larry will show you what's actually being turned off. When you turn off the AFCS, what you are doing is turning off and depriving the hydraulics to the integrated lower control actuators, and you are turning off the dash electrically. Now, why is that important to understand, gentlemen? Why is that important to understand? That all you're doing is depriving it of hydraulics and turning off the dash.
The rest is still working.
Okay. What do you mean, the rest?
Vertical gyro's still working.
Okay. Okay. But that's not part of the advanced flight control system. That's just a signal that's being processed by the AFCS. But what is still working that we do have to be concerned about? The LCTs. Very good. That's always a concern that people always ask. Well, when I'm turning off the AFCS, does that mean the LCTs are turned off? No, because we always need those. We always need those, so those are not turned off. Later on, we're going to talk about some characteristics of the AFCS, turning it off and then turning it back on, that you have to be aware of. We're also going to talk about some procedural. Why do we do things the way we do it in this aircraft? That are going to be related to that. And you'll see as we go along, we'll talk about those. Okay? Down in the bottom left-hand corner, you have your cyclic trim. When we talk about cyclic trim, what exactly are we talking about? The LCTs. Okay? Everybody gets a little frustrated that it doesn't say longitudinal cyclic trims. It just says cyclic trims. But they're still talking about those longitudinal cyclic trim actuators connected to the swash plates that we've already talked about several times. First switch we're going to talk about is your auto manual switch. In the automatic mode, the AFCS is programming both those longitudinal cyclic trim actuators. God bless you. Okay? In the manual modes, they're going to respond to those 2 switches, one marked forward, one marked aft. Extend and retract is how they're marked. Now, the thing you have to keep in mind is when that switch is in the auto position, they are both in automatic mode. When that switch is in the manual mode, both those longitudinal cyclic trims are in the manual mode. Which means what? Which means if you had one that was malfunctioning and you went to manual mode for that one, you now still have to control both longitude cycle trim actuators from then on out. Any questions about that? Okay. Next, top left-hand corner is your heading select. When you talk about heading select, when you engage heading select, remember, we're talking about the process. Up there, we talked about how it's working. What was the process for engaging it? First thing we had to do was identify command select. For the purpose of what?
Which HSI?
Which HSI do you want those computers to process the information from? Good. Then we have to adjust and know where that heading bug is. Do I have to line it up with the lubber line? No, I don't have to. As long as I know what? As long as I know what's going to happen by the time that I hit that heading select button on the AFCS control panel. Because if that lubber line's not lined up with that heading bug, or the heading bug's not lined up with the lubber line, as soon as you engage heading select, that aircraft will go into a turn. Based on the amount of desired change, will determine how much of a bank angle it'll go into, up to 20 degrees. Any questions about that? When we engage it, you will get a blue-green light that says engaged. Why blue-green light? NVG compatible. Any questions about heading select? And heading select, as long as it's on, that light will be on. If it's turned off or it goes off, that light will go out, telling you that it's out. Now the next two, you have barrel altitude hold to the left, rate altimeter hold to the right, controlling your altitude hold feature of the advanced flight control system. Keeping in mind, gentlemen, that if you do not engage altitude hold, this aircraft has no type of altitude hold feature automatically. I'll say that again. If you do not engage an altitude hold, there is nothing in the system that will maintain altitude for you automatically. So you have to engage it if you want it. Any questions about that? Now, barrel altitude hold is going to be based on barometric pressure. Rate altimeter hold is going to be based off of what? The what?
Should be your feed AGR, whatever.
Not what I'm looking for. What is the signal that's actually being processed for rate altimeter hold? No. What? Pilot's rate altimeter. Keeping in mind that the pilot's is the only true rate altimeter. Okay? The co-pilots is slaving off the pilots. The one in the hole, the flight engineers, is slaving off the pilots. And altitude hold is a feature of the #1 AFCS computer only. Altitude hold is a feature of the #1 AFCS computer only. Why is that important to understand? What happens if I lose the #1 AFCS computer? Well, you lose your altitude hold. You don't lose the rate altimeters.
Yeah, I know.
You lose the rate altimeter hold feature, which means what? You're going to notice a lot of operators' manual cautions and notes and warnings associated with the loss of anything on the #1 system because of that feature. Yes, sir?
In the beginning, you said that both AFCS are equal.
The computers are.
Yeah, okay.
It's the wiring that causes them to be different. Good point. Yes, sir. The computers are completely identical. Either computer can be in the #1 slot. Either computer can be in the #2 slot. It's the wiring and the inputs and the outputs of that wiring that provides for altitude hold. Now, Last but not least, the last thing you have to know about that switch, those switches, is they are electrically interlocked. Meaning what?
One's on, the other's not.
If one's on, the other's off. You cannot engage both of them simultaneously. It won't let you. If you had rate altimeter hold engaged, and then engage barrel altitude hold, rate altimeter hold will go off, barrel altitude hold will come on. Not the proper process, but that's where the electrical interlock comes in. You cannot have them engaged, both of them engaged simultaneously. Now we're going to look at your cyclic controls. You got your centering device release right here. Centering device release, we said that when we push this button, what's going to happen?
Magnetic brakes. Pitch,
You're releasing the mag brakes on what?
pitch rolling in.
Pitch, roll, and yaw. Everybody understand that? We talked about that under flight controls. But it also has an AFCS function. What is the AFCS function? It's going to momentarily interrupt heading hold, and it's going to momentarily interrupt bank angle hold. Why? If I push this button, what is my intent, gentlemen? That you're going to make an input. Do you want to have to fight the hold feature that was made to help you? No. So therefore, by pushing that control centering device release, you're also releasing and momentarily interrupting bank angle hold and heading hold. Any questions about that? AFCS trim switch. AFCS trim switch, although we call it the AFCS trim switch, it actually is operational laterally as well as longitudinally. Laterally, what is the requirement for the advanced flight control system? To be on. It has to be on. Longitudinally, what is the requirement for the AFCS? It doesn't matter. It can be on or off. It's still going to work. Now, laterally, you have to be aware you can roll this aircraft all the way over. The only limits of this system are the limits that apply to you. So you can take it all the way into a 60-degree bank turn. Now, and they will show you. They will allow you to roll it into a 40, 45, maybe even a 50-degree bank. They want you to see that when you do that, your cyclic stick position is not going to move at all. Why? Where did we say the input was for the advanced flight control system? The what?
The AFCS portion.
Okay. From the AFCS, it goes to where? The ILCAs. Keeping in mind that anything that occurs at the ILCA is only going to manifest itself on the output side of those integrated load control actuators. So what are you going to see, feel, or know on the controls? Nothing. It's not going to move the controls at all. Any questions about that? Where if I increase or decrease the airspeed using the AFCS trim switch, what am I going to see? The aircraft's actually going to move. Why? Because you're moving the cockpit control driver actuator, which is located below the integrated load control actuators. Any inputs that occur below the ILCAs, the integrated load control actuators, are going to manifest movement in the controls. Anything that happens at the integrated load control actuators is only going to manifest itself on the output side. So you won't see any movement or feel any movement on the controls. Questions? Looking at the thrust control trigger. We talked about the thrust control trigger. We said that it does what? It's going to release the mag brake. But we also have to talk about the fact that if you have altitude hold engaged, and I'll say that one more time. If you have altitude hold engaged, then what will happen also when you push this thrust control trigger, you will momentarily interrupt altitude hold. Again, why momentarily? It will allow you to adjust your altitude, and then as soon as you let go of that thrust control trigger, what do you want the system to do for you again?
Re-engage.
You want it to re-engage. And it will do that for you, gentlemen. Meaning what? Meaning in order to change altitude, if you engaged altitude hold, you don't have to physically reach down there and turn it off. You can go ahead and just leave it on. Now, here's the catch-22 though. It does create a new phenomenon that you're not used to. What is the new phenomenon? The new phenomenon is you're used to, in a lot of your aircrafts, establishing a rate of descent or establishing a rate of climb, leaving it there and letting the aircraft do what it's supposed to do. With altitude hold engaged, it's only going to allow you to do that for as long as you hold the thrust control trigger. Meaning what? Now listen, gentlemen. I'm just trying to paint a picture. Nobody's done this to the best of my knowledge, but I need you to understand. Here's what's going to happen, okay? If I have a 1,200 foot rate of descent and I had altitude hold engaged on, I've got a 1,200 foot rate of descent engaged, I let go of the thrust control trigger somewhere in there. My aircraft weighs 48,000 pounds. What do you think is going to happen in response to me letting go of that thrust control trigger?
A lot of noise.
It's going to sound bad. But what's going to happen is momentum is going to keep on trying to carry me through. Okay? You can't just stop it like that. But what's the system going to try to do?
Capture it.
It sure is going to try, though, isn't it? And it will overspeed, over torque, over temp. It will do whatever it has to do to get back to that altitude that you told it to maintain. Now, if I want to establish a rate of descent, can I? Sure. What do I have to do? Just disengage, deselect, altitude hold, and this aircraft flies just like any other aircraft. Any questions about that? Now, there's an operator's manual caution associated with it. Could somebody just please read that for me? Anybody? Nobody wants to read?
I'll read that.
Okay.
The operator's manual caution to prevent engine overtorque, do not enter forecast moderate or stronger turbulence with the thrust brake portion of the CCDA inoperative.
Okay. Now, incorporated into that cockpit control driver actuator, we said we had our magnetic brake. If that magnetic brake's not working, you do not want to enter moderate or stronger turbulence. Moderate or stronger turbulence. That minor stuff doesn't affect us. Why? Because now you're going to have to sit there and you're going to have to try to maintain altitude in this aircraft. And you're not going to have anything holding that thrust control in place. You're going to have to do it all. So it'll become a lot of work. But keep in mind, in anything in this aircraft, if you have to write down turbulence, you've got to give the descriptive adjectives. In other words, you have to put moderate or stronger. Any questions? Master caution / advisory lights. These are master caution lights. Okay, you got AFCS 1 and AFCS 2. They are going to come on for any of the following reasons. We lose our vertical gyro signals. Keeping in mind that we already said that the number 1 vertical gyro is connected to the number 1 AFCS. So if I lose the number 1 vertical gyro, then I will only turn on the number 1 AFCS light. Does everybody understand that? Okay, if I lose the number 2, then I'll get the number 2 associated light. We pretty much already emphasized that under instruments too. Is there any questions about that? If we lose hydraulic pressure, we're going to lose the associated AFCS. Again, number 1 flight control hydraulics, number 1 AFCS. And then, of course, last but not least, if we lose the electrical system. Number 1 AFCS. So we're going to lose the associated system. Now, in talking about the AFCS lights, the next thing we have to talk about is you'll notice in your checklist there's a funky place to check the AFCS, isn't there? We don't have the rotor blades turning, the aircraft's on the ground, yet we're checking the AFCS. Why? And what am I checking for? One, all you're doing is checking the system. All we're doing is checking lights. But there's another very, very important function going on that you need to be aware of. You're repositioning the dash. Did everybody hear that? You are repositioning the dash. Now, why would I have to reposition the dash? And you're probably going to experience it here at Mother Rucker. Okay? Here we go. I'm the IP, and we're taking Jeff out here. Man, Jeff's doing a great job. First thing I'm going to have Jeff do is back down to 100 knots. I need you to back down to 100 knots. He's going to back down to 100 knots. I'm going to look at him. I'm going to say, you ready? He's going to say, heck yes. And I'm going to identify the AFCS system select switch. And I'm going to verify one more time. You ready? He's ready. Okay, AFCS system select switch coming off. And I'm going to turn it off. He does the typical stuff. You know, it gets a little squirrely on him. But he gets it under control in a reasonable amount of time. Doing a great job. Let him fly around a little bit, get comfortable with it. Okay, let's go ahead and shoot our approach. He shoots his approach, he comes in and he lands. Okay, we're at the end of our time. Let's go put her in parking. Okay, so what are we going to do? After landing check. After landing check, it's one part of the after landing checks. AFCS system select switch off. Well, guess what?
It's already off.
It's already off. And so we go and we put it into parking. And now, pat each other on the back. Great job. Phenomenal. Now, we get ready and we take the good captain out, right? Okay. Different time, different crew, different everything, right? I don't know where they left it, did I? Where's the dash currently programmed right now on this aircraft? Being the same aircraft that he just flew. 100 knots. What's the airspeed of the aircraft? 0. Not a very good combination, is it? So besides checking the system, the other thing that's going to happen is that dash is going to reposition. Now, is it important to know that the dash is repositioning? Sure it is. We don't want to do anything until it is repositioned, don't we? So therefore, as pilots, you have to be able to identify that that process is occurring. And understand that that process is occurring. So what's going to happen? Okay, we're going to check AFCS. And when we go to check AFCS, whether it's off to the left or off to the right, we're going to go ahead and presume that it's off to the left. Why are we going to presume that it's off to the left? Because pretty much that's what everybody does. Why? Because then it's easier just to go 1, both, 2, off to do your check. And we know what lights we're looking for at that point. Agreed? So we're going to presume that it's off to the left. And we're going to select number 1 system. What is going to happen is that number 1 AFCS off caution capsule is going to stay on. Note the key word. Stay on. Remain on. Be on until that dash motor has repositioned. Notice what I said. Until that dash motor has repositioned. Why? Because by selecting the number 1 system, the only motor I am actually currently operating is the top motor of that dash, as per what we learned in flight controls. Agreed? So now, when will I know that it's repositioned? What? The light will finally go out. Up to how long does the light have to go out? 30 seconds. That's why, gentlemen. That's why. Any questions about that? And now I'm going to select both. And what's going to happen? Number 1 AFCS off caution light's already out. So now what's going to happen?
Number 2 is going to go out.
Okay, it's going to remain on, stay on, be on until that motor has repositioned. Now notice, what am I avoiding? I'm avoiding the word comes on. Why am I avoiding the word comes on? What does comes on imply? No, not that there was a failure.
It was working before.
No. Comes on implies that the light was out. Did the light ever go out? No. The lights are already on. So when I selected number 1 and it was adjusting that motor, repositioning that motor, the light remained on and then went off. It wasn't off, came on, and then went back off. You understand the difference?
You're saying there's no instance when I'm doing this check on the ground, when I turn it to 1, that it'll be off. It should always be on, stay on until that recenters, and then it'll go out.
Yes, sir.
Unless
Now,
it's failed state.
huh?
Unless
Unless it fails. Or, now, it has up to 30 seconds, but if that dash was already repositioned, when you select number 1 AFCS system select switch on, it'll go out relatively quickly. Meaning what? Meaning the dash was already positioned. Okay? Reality is, the only major place that you may encounter this to any degree is here. Why? Because most of the time we don't fly AFCS off just to fly AFCS off. So Mother Rucker's the only place that you may see that a little bit. Any questions? Okay, so now, here we go. We take the good captain out. We didn't set him up for failure. The dash is repositioned. We go out and fly. He's doing a great job. Ready for AFCS off? Sure. What am I going to tell him to do? Back down to 100 knots. Why? Because unit SOP here at Mother Rucker says that you have to be at 100 knots or below to turn the AFCS off. So we're going to back down to 100 knots. AFCS system select switch identified. You ready? AFCS system select switch coming off. Now we go out and we fly. Okay? It gets a little squirrely, but he gets it under control relatively quickly. See, we don't have to be nasty about that. He can do fine. We can still accomplish the training. Okay, he's doing a great job. And now He's proven that he can fly AFCS off just as well as he can fly AFCS on. Now we're ready for the next stage. We're going to go do a sling load. Okay, so what do we have to do now? We have to turn it back on. Why, sir? In order to hook up the load, it is required to be on. Okay, now, he's flying faster than 100 knots now. AFCS system select switch identified. You ready for me to turn it back on? Please turn it back on. Okay, coming back on. Now, what's he going to experience on the controls? What?
Pitch transient.
Pitch transients. Now, because I said it was 100 knots, and I said that he was going faster, you could actually tell me that the aircraft's going to do what? It's going to pitch up, and then it's going to pitch down. Why? Because initially it's going to go to slow down. And then they'll meet somewhere in the middle. So it'll kind of pitch up, and then it'll pitch down. If I don't give you airspeeds, the only thing you can tell me is you're going to experience pitch transients. As a result of what? As a result of what? As a result of the dash where it was versus where it is now, and those motors are incredibly slow. Okay? So you're going to have, because it's slow, you're going to experience some type of pitch transients. Unless you go back to 100 knots and turn it on, where you turned it off. Then you may, it may be so slight you may not feel it. Yes, sir?
What does it do with the thrust control?
It doesn't do anything with the thrust control.
Will you maintain the same altitude?
It depends on the severity of the changes. If it was at 100 knots when you turned it off, and you decide you're going to turn it on at 160, then you may have to make some power changes to accommodate.
Okay.
But if you were at, it may not be so drastic that you don't have to worry about too much power changes.
And if you get your altitude hold engaged,
Mm-hmm.
then it probably will maintain that altitude.
Yes, sir. It would automatically do it by itself. Yes, sir. As long as, again, it's not too extreme, and we'll talk more about that as we go along. But you're tracking. You're picturing it right. You notice again, may, might, could, may. There's a lot of that in this. Why? Because depending on the severity, you may have to make some minor changes. You may not. So that's why there's no real set answer. You can anticipate if it's a major change, then you would probably have to make some power changes. How bad? Depends on the severity. Anything else? Any questions about these lights? Now, unfortunately, we've got to go one more step. And that is that I would say probably a good high 80s, maybe impossible low 90s % of our AFCS problems don't have anything to do with those lights. Meaning what? Meaning that you may have to do a little bit of troubleshooting. Because what will happen, normally with the advanced flight control system, you will encounter some type of transients. Pitch transients, roll transients, yaw transients. If altitude holds engaged, maybe altitude transients. If it's altitude engaged and you're encountering altitude transients, then you know automatically it has to be which system causing the problems. Number one. Are we tracking? We good? Okay, but for pitch, roll, and yaw transients, you may have to do a little bit of troubleshooting. In the CH-47 aircraft, it's okay. Not only is it okay, it's expected. Okay? If you encounter AFCS problems, AFCS is not working, you bring that aircraft back, and you take the log book and throw it into maintenance hand, guess what you need to be ready to do? You need to be ready to go fly. Because now, That maintenance test pilot's not going to want to daily and pre-flight that aircraft again just because you didn't do what you were supposed to do, which is figure out which system was causing the problem so that you can give them more information. Okay, how do you do that? If you encounter pitch, roll, yaw, transients, then what you're going to do is you're going to select from both, select one of the AFCS systems. Now what you're going to see in the handout is that if you encounter a hard over, if you select the good system, then you're going to anticipate a reverse hard over. Keeping in mind, how many ex-Huey drivers do I have? None? Okay, cool. When we say a hard over, all we're trying to do is give you a describable action so that you can do what in return? Give us a describable action back. Okay? So if I anticipate a hard over, if I select a good system, I'm going to anticipate a reverse hard over. Does everybody understand that? And even the Dash 10 uses that terminology. And then you can write up aircraft experience, pitch transients in number 1 AFCS system. In flight. Okay? So now, they know where to start. We're going to troubleshoot the number 1 AFCS computer. We're going to do all the ground tests for the number 1 AFCS computer. And we'll try to figure out what's going on. Okay? But if you don't troubleshoot that, then they're going to have to go out and fly the aircraft again and do what you could have done. In this aircraft, turning the AFCS off does not constitute an emergency procedure. I'll say that again. In this aircraft, turning the AFCS off does not constitute an emergency procedure. You can turn it off anytime you want. It's kind of a catch-22 though. What's the catch-22? In order to turn it off, you got to be good. In order to get good, you got to turn it off. And unfortunately, unless you're the pilot in command, you've got 3 other voices on that aircraft that may be saying, "Come on, Captain, do you have to fly with it off? You got nothing to prove," you know, because I'll tell you right now. Now, I don't recommend you do this if you're the one on the controls, but look through the rear view mirror, and you will notice AFCS off, how bad that back end is moving back there. Okay? And you will get an appreciation of just what's going on in the back. Any questions about that? All right. We're going to look at the components of the AFCS. In looking at the components of the AFCS, it's going to consist of your horizontal situation indicator. Of course, your caution/advisory lights on your master caution panel. Now, right here on this diagram, and I know it's wrong in your book too, you'll notice under cockpit control driver actuator, what does it say beside it? Pitch and thrust. What is the problem with that, gentlemen? What do we need to do to that picture? What? What'd you say, sir?
I said scratch pitch. But
I think you should scratch pitch too, because pitch is not part of the AFCS feature. So the only cockpit control driver actuator that we're going to be talking about is the thrust. Does everybody understand that? The integrated lower control actuators, how many of them are we going to be talking about? How many? 3. Why 3? Pitch, roll, and yaw. What do pitch, roll, and yaw all have in common? Why not the thrust?
It is a dash.
No, the thrust doesn't have the dash.
Driven by the CCDA.
What?
Driven by the CCDA.
The thrust is driven by the CCDA, the cockpit control driver actuator. I agree with that. But what does the thrust integrated lower control actuator, what makes it different from the pitch, roll, and yaw? What doesn't it have? The extensible link portion. Remember, you got a boost portion of those integrated lower control actuators. You have an extensible link portion of those integrated lower control actuators. The only portion that's owned and operated by the advanced flight control system is the extensible links. So that's the difference. And remember, they'll ask you, how many ILCAs do you have? You have 4. Then they'll ask you, how many extensible links do you have? 3. And then they'll ask you what? Which ones have them? Which are what? Pitch, roll, and yaw. We tracking? And then you got your landing gear proximity switch. We'll talk about the AFCS features. You got your static ports and PDOT tubes and side slip ports. And then, of course, your 2 AFCS computers and your controls up in the cockpit. And we're going to talk about all those inputs and the controls. First one we're going to start with is the integrated lower control actuators. And talking about the integrated control actuators, we're going to talk about the features that they're going to provide for. All of them are going to provide for stability about all axis. Meaning what? Meaning motion dampening. Correcting for forces acting on the aircraft. That's what we mean by stability about all axis. And it will do it automatically. And in most cases, it'll do it without your knowledge. Why? Because the corrections are going to be made at these integrated lower control actuators, which in being made at the integrated lower control actuators, we know that the portion of the integrated lower control actuator that's going to be affected is only which portion? The upper, the output. So therefore, you will not see it or feel it. Now, in order to understand the advanced flight control system, the easiest thing to do is relate it to something that we're already pretty much familiar with, and that is a car. A lot of people get frustrated when I do this, but you'll see why I do it this way. Here we go. Tom gets to drive a Ferrari. Why? Because this is my example. Okay? So I'm going to be driving a Ferrari. I'm going to be driving it down a road that is about as straight as it can come. And I'm going to be driving 180 miles an hour down that road. What am I going to have to be doing in this Ferrari still? Am I just holding that steering wheel? I'm going like this, ain't I? Why? What am I correcting for? I'm going down a straight road at 180 miles an hour, so what am I correcting for?
Input from the outside.
Input from the outside, in the case of a car, caused by what? Road conditions. Even though it's a Ferrari, yeah, I chose a Ferrari for a reason. At 180 miles an hour, you think wind's still not going to affect it? Sure, winds are still going to affect it. Wheel conditions or tire conditions. Balance. There's a lot of factors that come into play, which is resulting in me, even though I'm in this slick, low car, going 180 miles an hour on a road that appears to be as straight as can be, and I'm still going like this. Well, guess what's happening in this aircraft, gentlemen? And here's where it's kind of freaky. Now I got a multi-million-dollar airplane at altitude with a whole lot bigger airframe and a lot more wind acting on it and a lot more conditions changing on it, and I'm flying like this. Hey Jeff, how you doing, man? How's the family? You know, I'm flying like that. Why? What do you think's happening in that flight control closet? If you were to look at the output portions of those integrated lower control actuators, what you would see are those flight controls going like this. Why? Because they're having to do all the adjustments for you. That's how sophisticated this system is. Just to also help you understand how sophisticated it is, the first time that we took the CH-47D, I say we like I had anything to do with it. First time they took a CH-47D and landed it on the deck of a ship. First thing you have to understand is if you've never landed on the deck of a ship, those Navy people are fast. You get all four landing gear in this case down on the ground, you're chalked and chained just like that. Don't blink. Okay? Well, the first time they put a D model Chinook on the deck of a ship, what did they forget about? The AFCS. What does a ship do naturally? It pitches, it rolls, it yaws. What's this system? Stabilize, pitch, roll, and yaw. So guess what the aircraft did? Snap, snap. Pilots got on the controls, snap, snap. Luckily, the only thing they did was change and some minor damage to the gear. They didn't do any damage to the deck. Otherwise, Navy's not a great fan of the Army landing on their ships already, but they're getting better. Okay? So that's how sophisticated this system is when we talk about stability about all axes. Any questions about that?
Do you have to make those landings AFCS off?
No, they still make it on. They just have to turn it off quick.
Proximity switches don't degrade it at all, or?
It only reduces one axis. It only affects one axis. Okay? Unlike the Black Hawk with the weight on wheels, ours doesn't turn our system off. And it doesn't degrade it in all the axes. It only degrades it in one.
Which one?
Pitch. And we'll show you why and explain why here in just a second. We're going to talk about them here shortly. Okay? Now, next thing is going to be bank angle. What extensible link portion, which ILCA, integrated lower control actuator, is going to be associated with the bank angle, maintaining bank angle? The roll integrated lower control actuator is going to be used to maintain bank angle. And it's going to do it automatically. Okay? Bank angle trim is going to be a feature of which ILCA? It's not a trick, gentlemen. It's not a trick, so don't be afraid to answer. It's part of the roll, ILCA. In other words, what? What is bank angle trim? Bank angle trim is the ability to make changes to the lateral axis of this aircraft using this AFCS trim switch. Although they're going to show you the full range of motion, reality is most people just use it to make minor changes. That's all they do. Any questions about that? Now, heading hold is part of what? Which integrated lower control actuator? Yaw. And we already drew this picture up there and said that it's a directional gyro signal directly to the AFCS to the yaw integrated lower control actuator. Now, the next thing we have to talk about gets a little bit more complicated. Why? Because we have heading select. Heading select is actually going to make inputs into how many of your ILCAs, your integrated lower control actuators?
Say two.
Two. Why?
Roll in the yaw.
The roll and the yaw. For the purpose of what? Coordinated turn. But now you'll notice right below that it says coordinated turn. Well, wait a minute now. Didn't we just say coordinated turn is part of heading select? So why do we have an additional feature called coordinated turn? What in the heck is that?
When you make a turn.
What?
When you make a turn without using the heading select.
when you make a turn without using the heading select. In this aircraft, gentlemen, the only thing you have to do to change your heading or change your direction is roll it to the heading that you want to roll it into. You do not have a requirement to put in any type of pedal. Okay? As long as you are above 40 knots. And that's going to be applicable to both of those, heading select and coordinated turn. 40 knots is going to be a requirement. Now, you'll notice there's one more thing that we have to talk about that's not kind of highlighted. And that is the longitudinal axis of this aircraft gets very, very confusing. Because you'll notice we specified about the yaw extensible link. We specified about the roll extensible link. But which one did we forget? Which one did we not really highlight too well? The pitch. And I actually had somebody ask me this the other day. Because the longitudinal axis of the aircraft gets very confusing in the fact that what? The longitudinal axis has an integrated lower control actuator controlled via what? AFCS. It has a dash controlled via what? AFCS. And it has two longitudinal cyclic trim actuators controlled via AFCS. Okay? Now, I can tell you why the computer manipulates the ILCA. I can tell you why the computer manipulates the dash. And I can tell you why the computers manipulate the ILCA, or the longitudinal cyclic trim actuators. What I cannot tell you, and don't pretend to be able to tell you, is how it proportionally controls them all. And that's just the magic of the computer. Okay? So what does the AFCS computer use the integrated lower control actuator for? It's part of that stability about all axis. What portion of it? As I'm flying along, is it possible to have forces acting in the longitudinal axis of this aircraft? Sure. And what's the computer going to do? The computer's going to sense that, and it's going to correct for it. And it's going to correct for it at that extensible link portion of the pitch ILCA. Any questions about that? Now you notice I'm stopping there. Why am I stopping there? Because the next piece of that puzzle is the next thing we're going to talk about, which is your dash, which stands for differential airspeed hold. Why differential airspeed hold? Because it's going to provide for the following: airspeed hold above 40 knots, pitch attitude hold below 40 knots, and positive stick gradient. And then we're going to keep saying that over and over and over again. The top motor is owned and operated by the #1 AFCS computer. The bottom motor is owned and operated via the #2 AFCS computer. Show me the #1 motor, sir.
Is it interchangeable? I mean, can it be either or?
It can be either or.
So
He did the key. Okay? Reality is it can't, because what you'll notice is the rod ends are different. So one rod end will fit into the bell crank. One rod end will fit into the bottom portion of the extensible or the boost portion of your integrated lower control actuator. But the motors themselves are identical. Okay? So the captain did the right thing. As long as you vertical 1, 2. The top motor is going to always belong to the #1 AFCS computer. The bottom motor is always going to belong to the #2. Now, when we talk about, again, airspeed hold above 40 knots, we said it's going to process what to maintain airspeed? P-dot static, which is why below 40 knots it's unreliable. So therefore, do we want to help you maintain airspeed below 40 knots? Sure we do. But the only way we can do it is actually by maintaining what? Pitch attitude. The result of maintaining pitch attitude is still what? Maintaining how fast we're going. Hence, differential, D, differential, A, or SH, excuse me, AS, airspeed, hold. All we're doing under D is it's either going to process your P-dot static system or it's going to process your what to maintain pitch attitude? Your vertical gyro signal. We tracking? And then we said positive stick gradient is what? Nothing more than the ability to put in a forward stick position or a aft stick position, leave it, and know the aircraft's either going to maintain a forward airspeed or fly backwards. Any questions about that? CPT. We already talked about the CPTs, didn't we? The control position transducers. The control position transducers are in there for what process? Why do we need the CPT? What did we say under flight control class? It quite simply tells the advanced flight control system was a pilot-induced movement made. Why? Because if it can't distinguish between forces acting on the aircraft and a pilot-induced movement, how does it know whether to correct or not correct? How does it know whether to allow for the movement or correct for the movement? And that's why the system has to tell itself, hey, did a pilot-induced movement occur? And that's the job of the CPT, control position transducer. Now, listen to me carefully, gentlemen. How many CPTs, control position transducers, do we have in this aircraft?
Three.
Okay. And man, the bus got it down pat. The book says 3. Why does the book say 3?
Pitch, roll,
Pitch, roll, and yaw. Why does it specify those 3?
because the thrust is induced by something else.
Okay, I'll allow him to bail out that way. We haven't covered engines yet. Okay, we did cover it under flight control class, and we said that the CPT for the thrust is actually talking to the digital electronic control units, which is the computer system for the engines. That CPT has nothing to do with those advanced flight control computers. So it's not processing that information. Understood? Good. And you have to pay attention. And because I asked the question here during this class, the answer is 3. Okay? Now, if I just threw the question out there and we weren't in the middle of a class, then you would need me to specify what? What would you need me to specify in order to answer the question?
Which system?
What do you mean, which system?
I'm saying as far as what the function of the CPT.
No, not what I'm looking for. If I were to just throw it out, we're not in AFCS class, we're not in engine class, and I just say, how many CPTs do we have on the CH-47? What would you need from me to give me the correct answer? What engine type are we talking about? Because the CPT for the thrust axis is only associated with the 714 engine. Okay? And that's where I want to make sure you're not confused. The CPTs that we are currently talking about are at the very, very bottom of your flight control closet. 2 of them on the pallet at station 120. 1 of them on the pallet at station 95. The yaw on pallet 95 the pitch and the roll on the pallet at station 120. Everyone tracking? Proximity switches. Gentlemen, what you're going to find out is we have 2 proximity switches. We have one on the aft left landing gear, and we have one on the aft right landing gear. Question? Go ahead, sir. What's your question?
Oh, I was just wondering where the CPT is for the 740 then.
For the 714, it's up a little bit higher in the flight control closet. Okay?
It is on the pallet.
It's not mounted. It is mounted to the pallet per se, only because it has a little standoff, but it's not really associated with the pallet. All it is it's connected to that bell crank for the thrust axis, and it just goes up and down, and as it goes up and down with your power changes, it has 2 cannon plugs, one going to the number 1 engine deck U and one going to the number 2 engine deck U. I mean, they're all 3 of them, excuse me, all 4 of them are down low in the closet. The thrust one is just higher than the other 3. The other 3 are all equal in height. The thrust will be slightly up. Good question. That's a very good question. If you go back through your handouts and you look at where the droop eliminator potentiometer is for the 712, it takes the place of that component. Good? Okay. That's a good question. Anything else? Okay, now we were getting ready to talk about the proximity switches. You have 2 proximity switches. And the way the proximity switches are mounted, we're really going to test my artistic ability today. This right here is the aft landing gear area. What you have right here is a drag brace. And then right here would be your aft landing gear. Mounted to this drag brace is going to be a little connecting rod. That connecting rod is connected to that target, and it has small holes in it, and all they're trying to do is just make it a little bit lighter. Okay, that's all they're trying to do. So when we pick this aircraft up, what's going to happen is as this aft landing gear breaks the ground, this whole drag brace system is going to come down, pulling on this connecting rod, which is going to cause this switch under here to be uncovered. We tracking? Everybody see that? When we put it back on the ground, the opposite's going to occur, which is going to cause this switch to be covered. Now, as a result of that switch being uncovered and covered, and you can see the switch, there's the switch itself. This is called the target, and this is that connecting rod that we're talking about. This is connected to the target. The bottom portion will be connected to the drag brace. Everyone see what's happening? Okay, so when this aircraft breaks the ground, that target's going to pull away, uncovering that switch. As it uncovers that switch, the following is going to occur. It's going to send a signal to the AFCS computer telling the computers that we are off the ground. Therefore, it's going to cause those computers to do what? Tell those longitudinal cyclic trim actuators to do what? Level off. Why? Because it can't process airspeed yet. Why not?
40 knots.
We're below 40 knots, so the PDOT static system's unreliable. So it needed something else to tell this aircraft that we are on the ground or off the ground. We tracking? Now, when we put the aircraft back on the ground, when both those targets are covered, note the key word, when both those targets are covered, and that switch is open, what is going to happen are both those LCTs are now going to go back to the what position? Ground position. Now doing what? Allowing the 9-degree and 4-degree tilt of the transmissions to re-influence the rotor system. For allowing what?
Ground taxi.
Ground taxing, ground handling of the aircraft. Any questions about that?
What's the is it an electrical signal or is it magnetic?
It's an electrical signal.
So what? How's it? I mean, just by looking at that picture, the target is made of what? Is it just,
It's just a metal alloy. It's
and then what is the pickup on the other side? Is it actually being compressed?
no, you know what? Let me recant that. Okay, let me double check what it is to be sure. Okay, because I think it is magnetic. It is magnetic, but it's opening and closing a switch inside the computer is what it's
There's
doing.
probably a resistance there because they call it proximity. It covers not all of it. I mean, there's a resistance there being.
Created. Yeah, I need to verify. I don't want to give you wrong information. Yes, sir.
What will happen if you do a pinnacle landing, after landing gear on, front off?
Okay, which is why, and you're leading us right down what we're getting ready to talk about. Okay, only I was going to ask you, why do both those switches have to be closed to tell the LCTs to go back to the ground box? Why is the requirement for it to be both closed?
Because you might be busy with the slope landing.
What?
You might be busy with the slope landing.
You might have a slope landing. And what you're going to find out when we talk about these proximity switches, the left proximity switch does everything through the number 1 AFCS computer. The right proximity switch does everything through the number 2 AFCS computer. Which means what? If those switches only is closed on one side and they were allowed to program just their rotor system, you would have one rotor system go into the retracted position. You would have one system in the tilt position, and that would cause a vibration and a conflict, and then you would end up tearing up or putting stress on the aircraft. So basically what they did is based on slope landings or pinnacles, depending on what we're doing, they made it so the requirement is both those switches have to be closed to go to the ground position. That way you don't have one retracted, one extended.
So the left side goes to the number 1.
Yes, sir?
What if the left side doesn't connect with the AFCS?
If it fails,
Yeah.
then the chances are, what?
But we do have 2 wheels on the ground.
What will happen is we will get another associated light on the maintenance panel telling us that one of them's not working. And what the pilots can expect out in the front is that their LCTs won't work. And therefore, they're going to end up doing what as a result of it? They will end up manually programming them. And we're actually going to end up talking about all that in a little bit, because there's several reasons why you will have to manually program them. Okay, but you're tracking. You're on track. Anything else? Okay, now, as per the question earlier, when we have the proximity switches on the ground, what you're going to find out is only the pitch axis is reduced by 50%. Why? Because when we're on the ground, we don't want to accidentally hit that cyclic, causing a hard over and put that forward rotor system into the ground. That's only one part. There's a new concept that you're not aware of yet. You will be aware of it pretty quickly. In this aircraft, we can two-wheel taxi. We two-wheel taxi with the AFCS on. If the longitudinal axis of this aircraft was not reduced if the sensitivity was not reduced, what would happen as a result of us trying to two-wheel taxi is the aircraft would porpoise. And it would get really funky. And that's why, the other reason why they had to reduce the pitch sensitivity by 50%. Good? Now, here's my next one. I like to talk about the next one. In reality is, I've given you all the facts you need to know to kind of figure out what's happening. You're going to notice the other thing that's going to happen as a result of those switches is that it's going to cancel the pitch CPT input into the advanced flight control computers. It's going to cancel the pitch CPT input. How many CPTs did we say we had? 3. How many is it going to cancel?
Pitch.
1 pitch. Why? Here's what's going to happen, gentlemen. The reason why we have to cancel the pitch CPT input is for a certain feature, which is what? Can anybody think about why would I want to cancel the pitch CPT input? First off, what does the pitch CPT input do for me? What does it do for my system? Say it.
The dash
What about the dash?
was extract.
The dash will program to what? Airspeed hold above 40 knots. Pitch attitude hold below 40 knots. What's a slope, gentlemen?
It's a pitch attitude.
It's a pitch attitude. What do I want the system to allow for? I want it to allow for that programming, don't I? But where did that signal come from? Where did the program of the pitch attitude of the aircraft, where did that signal get produced from?
Vertical.
Vertical gyro. Is that a pilot-induced movement? No, it's a component-induced movement. So therefore, if it did not cancel that pitch CPT input, it would initially allow it as a result of what you're telling the system to do, but then it would immediately take it away because what maintains it is a signal from the vertical gyro. Good? And then last but not least, it will turn on and turn off your ground contact lights on the maintenance panel as a result of those switches opening and closing. And that's just a visual reference for the crew member in the back, because basically your reference for that up in the cockpit is what? What's happening to the LCTs. So that way, if the LCTs are not retracting like they're supposed to, or they're not going to the ground like they're supposed to, we can specifically identify which one is the culprit in not allowing it to happen. Now, the right proximity switch has 2 additional features that are not AFCS related. The 2 features are, it will prevent accidental firing off of your M130 flares while you're on the ground. The other feature is that it will hold or allow for the hold feature of mode 4. Meaning what? What is mode 4?
Your IFF key.
That's your IFF. Now, it allows for the hold feature, meaning what? Meaning when you land this aircraft, if you take your transponder and you go to the hold position, it will hold that key. If you land this aircraft and don't go to the hold feature, as soon as you power down the aircraft, what's it going to happen to that key? It's going to dump it. Okay? It's going to dump it. Why? Because a controlled landing, commonly referred to as a crash, could result in those proximity switch is still being collapsed. And we don't want it to automatically hold that code. So therefore, you still have to go through the process of going to the hold position. If you do not, the result is it will still dump the code. Questions? Now, some additional facts that we need to talk about. What are the additional facts? If I am ground taxiing on an unapproved surface, uneven surface, what may you experience with the aircraft?
You probably got those independently opening and closing.
Exactly. You may have those opening and closing, which means those LCTs may be going from the ground retract, ground retract, ground retract, ground retract, ground retract, and you may end up having to do what to the controls? You may have to manually control them to the ground position. We already talked about water landing. Why? Because those proximity switches are not being collapsed. You may have to manually program them to do what you want them to do. If you're landing on a pinnacle landing or a slope landing, if you don't have enough aft cyclic to keep those switches down, you may have to pull in a little bit more aft cyclic, or you may have to do what? You may have to go to manual. Any questions about that?